Okay, so for this green box, I know that I've skipped it this time and last time. I've done that intentionally because on each of these pages there's so much information that I think that we should focus on what we need immediately to do the problems, and we'll do this box when we work on review problems next time. So we'll talk about the green box once we look at some review problems for this unit. So that being said, we are now moving into the calculation portion of this lesson, and this is what I think is the most interesting about these lessons. So this time we're talking about bottling soda. A bottling company uses a filling machine to fill plastic bottles with cola. The bottles are supposed to contain 300 milliliters. In fact, the contents vary according to a normal distribution with mu 298 and sigma 3. So they're supposed to contain 300, and I'm assuming that what is happening with the machine is they're setting the values of the machine that actually fills these bottles at 298 to give themselves a little bit of room for error. Does that make a little bit of sense? Okay. First question is, what is the probability that a randomly selected bottle contains less than 295 milliliters? So I'm assuming that would be too little. Like that would be too, what's a different way of saying that? That would be not enough cola to send to the distributor. It would be too low. One thing that is extremely important that you understand from this problem is that N is 1. You are not taking you are taking a sample, but the sample size is only 1. You are taking 1 bottle from the distribution. So we are not looking at an X bar, we are looking at an X value. So here's what I mean by that. We took X, that's our bottle, from a normal distribution with 298 as the mean and 3 as the sigma. And you do not need to check conditions because they tell you this is a normal distribution. So they gave this to us. Well, what they're asking us to calculate is the probability that our 1 bottle will contain less than 295. Okay, well, that's the same as some z value. Well, hopefully we still have this post-it from last time, and our z formula is right there. You do need to show that calculation, so I just do it underneath. I make like a little equal sign, and I just write it underneath there. So my x is 295. My true mu is 298. And my standard deviation is 3. So I'm looking for the number of dots, essentially, that are less than, I'm getting -1. Can anybody verify that? Great. No, I ain't drawing that normal curve. Do you want to? Yes. Yes, sorry. I thought you were asking if we had to. I don't want to. Okay, so now we do our z-table. So we're going to the negative side. It's just negative 1.0. So 0.1587. If we want to write that as a percent, we can times it by 100 and get 15.87%. So it's not, it is, I guess I should say, it is plausible we would get a bottle that has less than $2.95. 16% of the time, we will get a bottle that's less than $2.95. We're okay on that? If we wanted to write out the probability, we would have to say the probability that a randomly selected bottle contains less than 295 milliliters is 15.87%. Do we want to write that out? I don't feel like I want to write that out. I'm going to skip that part. I'll write it out on the next one. B. What is the probability that the mean contents of 6 randomly selected bottles is less than 295? So the probability that we would take one bottle is about 16%. What's the probability that if we take 6 bottles, their average would be less than 295? So this time, n is equal to 6. So now we have to do X bar. We're no longer looking at a single bottle. We are looking at 6 bottles, and we're going to average it. We're going to add the milliliters in the 6 bottles and divide by 6. This sample should come, or I should say does come, from a normal distribution with a mu sub x bar, so a sample average that is equal to the true average. And your true average is 298. The sigma of this sample can be calculated as our true sigma 3 over the root of our sample size. So this is different than the last one because now we have 6 bottles and we're finding their average. Well, remember we gotta check all the conditions. So the first one is the normal condition. And I'm now going to use this guy as my guide. So my sample will be normal either by the central limit theorem, so CLT, or because the population is normal. So in this case, n is less than 30, which means that the population has to be normal, and it is. N is less than 30, but the population is normal. We'll get an example where n is greater than or equal to 30, and I'll show you what you put in that case. Mu, we just checked that we took a random sample and the bottles were randomly selected. So bottles were randomly selected. I forgot to calculate my mean. I mean my sigma. Did you guys calculate sigma? Okay, I'll calculate it now too. 3 divided by root 6. I'm getting 1.2. I think I'm just going to go 2 decimal places, so 1.22. Can anybody second that? Great. What do we check? 10% condition. So we ask ourselves, do we think that 6 is less than or equal to 1/10 of all bottles filled by that machine? Yeah. I'm just going to put a check mark. Yes. Writing out capital N indicates to your grader that you've actually thought about the fact that, yes, it is reasonable that 6 is less than 1/10 of all the bottles filled. They probably fill thousands of bottles with this machine. So this is us verifying that we can use the normal distribution. You're okay? Okay, so now we can do our calculation. What is the probability that the average of our 6 bottles is less than 295? Well, that's the same as the probability of some z-value, which we have to calculate again because our standard deviation is different. So we do 295 subtract true mu of 298 divided by sigma of 122. I get negative 245. Can anybody second that? Okay. Huh? Oh, I don't know. Did I round weird? Did you guys get that? Well, you don't need to yell about it. Ugh. Get a grip on your rounding, teacher. Carter's right, 246. Okay, so now we're going to go down to negative 2.4, and we're going to slide over to the 6. We get 0.0069. If I want to multiply that by 100 to get the actual percent, that is less than a percent. 0.69%. I find that to be kind of interesting. So what we just found is the probability that we would take one bottle and it would be less than 295 is 16%. But the probability we would take 6 bottles and their average amount would be less than 295 is like nothing, 1%. Basically impossible. That's interesting. To finish out this one, I'm going to write the probability as a statement because really for an A plus we should. This would be like A minus. A plus we would have to write it out. So the probability that 6 randomly selected bottles contain, or I should say, have a mean less than 295 milliliters is 0.69%. You're hanging in? So one of the biggest takeaways from this is they're trying to get you to distinguish or recognize. In this one, you're just taking one bottle, so you use the population info. In this one, you're taking a sample of 6, so you need to adjust the population info a little bit. Okay, next one is airline passengers. In response to the increasing weight of airline passengers, the Federal Aviation Administration told airlines to assume that passengers average 190 pounds in the summer, including clothes and carry-on baggage. But passengers vary, and the FFA did not specify a standard deviation. A reasonable standard deviation is 35 pounds. Weights are not normally distributed, especially when the population includes both men and women. They are but it says, but they are not very non-normal. Okay. A commuter plane carries 30 passengers. All right, so let's pick out some information from here. Let's see. It looks like our mean, assume that passengers average 190 pounds. I'm thinking that's going to be our mean. Then they tell us a reasonable standard deviation is 35. So I'm thinking that's sigma. And then they also tell us a commuter plane carries 30 passengers. I'm not sure what that is at this point. So I'm gonna wait to label that guy. I'm pretty sure this is mu and this is sigma though. A, explain why you cannot calculate the probability that a randomly selected passenger weighs more than 200 pounds. So this is n equals 1. The answer is we cannot use normal calculations if, I should say, normal calculations to find a probability find this probability because the population is not normal. It doesn't matter that it's not extremely non-normal. That doesn't even matter. What matters is our population is not normal, so we can't use the normal curve. All we know about our population is that he's not normal. We don't know if he's skewed or bimodal or whatever. So we definitely cannot use our normal curve. Is that making a little bit of sense? Yes? Okay. Okay, well now let's say we take a sample. So instead of just looking at one passenger, what happens if we decide to take a sample of passengers and find their average? Well, X bar should be normally distributed with a mean at the true value, so 190, and a sigma of 35 divided by root n. So I think n is the number of passengers because it says mean passenger weight. So that means the mean of the 30 passengers. So this guy was n. $35 divided by root n. I'm getting 6.39. Can anybody second that? No, because this time this is saying we can't calculate the probability of one passenger, but we could calculate the probability of all of the passengers because it's all 30 passengers. So n is 30. So in this case, it would have just been 35 if it was normal, because n is 1. Okay, this time we should really verify that these are true, because we know the population is not normal. So first one, I'm going to have to go back to my paper. Do we satisfy the central limit theorem? Central limit theorem is sample size has to be greater than or equal to 30. So yes, I'm going to say n equals 30, which is greater than or equal to 30. So CLT applies. Mu sub x bar. Does it explicitly state that our passengers are random? No. So what I'm going to say here is, hopefully, the passengers are a random sample. Hopefully they're chosen randomly. Or I guess you would say chosen for that particular flight randomly. But this is good enough. And then lastly is 30 less than or equal to 1/10 of all passengers of the airline. Probably. So our population would be everybody that flies on this airline. In fact, it might be everybody that's going to fly in general. Okay. Find the probability that the total weight of 30 randomly selected passengers, oh good, exceeds 6,000 pounds. Okay. Hint, to apply the central limit theorem, restate the problem in terms of mean weight. So what is our sample average? We would need to take 6,000 and divide it by 30. What is that? 200. So the average weight of our 30 randomly selected passengers, they want us to calculate the probability that would be less than 200, exceeds 200. So they want us to calculate greater than. I'm going to highlight that. Okay, so they are asking us to calculate the probability that our sample average, or our 30 passengers, will be greater than 200 pounds. That's the probability of z greater than some value. So 200 minus our population value of 190 divided by our calculated standard deviation of 6.39. I'm getting 156. Okay, remember, normal curve only gives us areas to the left. So this is the same as 1 minus the probability of z less than or equal to 156. So I go to 1.5 on the positive side, slide over to 6, and I get 9406. So the probability is about 6%, 0.594. You hanging in? So the last problem, which I will make a video of if you would like to see it, is exactly the same. In fact, I'll show the solution so that if you don't want to watch the video, you can just look at the paper. It's exactly the same, except for it adds in the element of, would this provide convincing evidence against something? So if you would like an example of that, I will put up a short video. But if you're feeling good about deciding if something is convincing evidence, you can, at this point, start on your can you do and finish your lesson question. I have been checking my email all night lately because I know that these two lessons are challenging. So if you have any questions, I am checking during the nighttime just in case you guys need help. Okay? Okay. Okay.